Hey, so these are some notes for 3.5 through 3.6. And the big distinction between what we were studying earlier in Chapter 3 and this has to do with the fact that we're going to alter our launch angle. We're going to institute a launch angle that's not horizontal, which is going to complicate the initial setup of the problem, but it's going to give us some long-term effects that are going to be very helpful. Okay, so first off, we need to understand that when an object is thrown or kicked, rarely is it launched at an angle of 0. Typically there is some sort of theta here. Okay? And we want to know how much of that is in the x direction. Call that v naught x. We want to know how much of that is in the y direction, v naught y. In order to do that, we need to know what the initial velocity was. We'll call this v naught. All of these problems are built structurally the same because we always start with the x-axis being our 0 or our flat, which means the v naught in the x direction, which we always need anyway, is the hypotenuse, v naught, times the cosine of our launch angle. And v naught in the y direction is always v naught times the sine of the launch angle. These two values are going to allow us to go about our kinematic problem solving. Sometimes it is that initial. If we're told, hey, it's at 13 meters per second and it's at 30 degrees, okay, let's say it's at 30 degrees, now I can figure out how much of that 13 meters a second is in the x and how much of it is in the y. So that's a really important part of the process for being able to go through our kinematics with our x and our y and building, our v naught x. We now have a way of finding v naught x when it's not clearly stated, but it's implied with a launch angle and a velocity. A couple other things to keep in mind. If you're ever asked about the final velocity of an object, okay, so it's flying, it's doing its thing, and it's going to come down and it's going to crash, right? It's going to hit the ground. As it hits the ground, we have to understand that there is a final velocity in the y direction and there is a final velocity in the x direction. So as we identify these two velocities, we have to realize that if we want the actual final velocity, it is the Pythagorean hypotenuse to those two values. Okay, it's not going to be just the x or just the y. It's going to be the combination of the two, just like it's a combination of the two at the beginning. Nothing really changes there. So understanding how we can separate the x and y components of the initial velocity allows us to go forward and solve these problems. That's about what we need to know in terms of how projectile motion changes. Now, if we go through and we're real careful about the application of these two formulas, okay, there is something that can come out of the kinematics that becomes actually quite useful. It's called the range formula. This allows me to predict the maximum distance that an object can travel given a certain starting velocity and a specific launch angle. Now obviously air resistance is going to impact that, but ignoring air resistance, the range that any object can travel, projectile can travel, when launched at a specific speed and angle will equal this. The initial velocity squared times the sine of 2 theta. There's a little double angle thing going on there, divided by gravity. Now that's gravity on Earth or gravity on the moon. It could be gravity anywhere. The less gravity you have, the further you can throw something, which makes sense to us. So if I said I wanted to throw something at 13 meters per second at 30 degrees, okay, and I want to know how far can it get, I would say that the range is 13 squared times the sine of 60. I double the angle, all over my 9.8 from gravity. Now you could call that negative or positive. Truth is, we're not worried about vertical. Range is all horizontal, and so we're assuming that we're going to end at the same height that we started at. So it shouldn't matter with the 9.8, but let's go ahead and check real quick. 13 squared times the sine of 60, and that's divided by 9.8. And that's going to give us 14.9 meters. So this can travel, a total of 14.9 meters, and that's something that can be predicted and then understood. We want to be able to make predictions about range of flight. This is one of the big questions whenever we talk about military. If someone wants to shoot a missile at us, the question is, once it runs out of rocket fuel, how far can it actually travel? And those are important questions for us to be able to answer, because then, we can understand the physics of safety and defense. The last thing that we need to talk about is this idea of relative velocity and relative motion. And it actually has a lot to do with the concept that when someone is moving horizontally, in one side, maybe in a side-to-side direction, but maybe they're on top of an object that's moving itself in another direction, if we were to watch them from above, we would see something more like this. They wouldn't be traveling just horizontally or just vertically. Their motion, while they'd be all horizontal on top of this object they're moving, maybe it's a raft, from a bird's eye view, we would see them moving in a diagonal. So the question is, how do we add these? It's just a Pythagorean group. The issue that most people have, let's say this is 12 and this is 8, okay, and we'll call them meters per second. The issue that most people have with this is actually the angle. Okay, we know that 8 squared plus 12 squared square rooted would equal my velocity. Okay, my actual relative velocity. But it's always about relative to what? So let's imagine that we're on a boat, okay? And here's the shoreline on one side, and here's the shoreline on the other. See the boat's going that way, I'm walking across the boat. If we asked for the velocity relative to the shore, we kind of think about the word relative as being measured parallel or from parallel to the shore. Since this is the shore, when I create this right triangle, I've got 12 this way, I've got 8 this way, and I've got my diagonal. I need to make sure the angle, the theta that I'm using, let's put a theta right here, and I'll put a Greek letter phi there. One of these is the correct angle for me, and one of them is not. It's important that we understand that we have to find the parallel side to the shore. And since this is the shore, over here on the right and left, I want to find the side that is parallel to that. Okay? And now that I know that's the parallel side, I want to pick an angle that touches. I already know about the 90-degree angle here, so it must be this angle theta. Given that information, I just do a tan inverse, excuse me, and I find theta. And that's what you're going to have to be able to do, but understanding there are two angles, and you have to pick the one that is parallel to its relative source so that we know where we're measuring from. All right, good luck, and we'll see you in class.